Hello, this lesson is for section 4.2, quadratic functions. We're going to do some review stuff, but we're also going to do something brand new that you guys haven't seen at all in 1991. So just for review, we're going to graph quadratics that are in vertex form. If they are not in vertex form and they're in standard form, we're going to complete the square to transform them so that we can graph them. And then finally, the new part for you is to find the maximum and minimum values for quadratic, but also quadratic-like functions. Okay? Alright, so let's start off with an explanation for standard form versus vertex form. So this is the one that you're probably used to seeing. We've done this a lot this year already. ax squared plus bx plus c. That's standard form. This function down here is our parent function, f of x equals x squared, and we can see our points here, 1, 1, 2, 4, 1, negative 1, or sorry, negative 1, 1, and negative 2, 4. Alright, now, when we see something in vertex form, we can very easily see the vertex because it's given inside the form, which is why it's called vertex form. So HK is our vertex here, and in our example problem, down here, I have a vertex at 1, negative 2, and I can read that just based off of the equation. I'm going to take the opposite of this sign and keep that sign here. So as you can see, when it's graphed, it's at 1, negative 2. Now, in both forms, this a value is something you want to look at right away. If a is positive, it will open up. So a is positive, it opens up. If a is negative, it opens down. And in both cases here, my function has a positive 1, and here it has a positive 3, so these are both opening upward. Now, if I were to look at this specific value in front of our a term here, since a in this case is greater than 1, this 3 here, now my function has been stretched. So I actually want to take a look at that and show you guys a table of values, or not a table of values, but a function that's going to be stretched or shrunk. Okay, so here I have the mother function y equals x squared. Let's say I increase the a value. What you're going to see is now your graph becomes a little bit narrower. If I keep continuing to increase that, I'm seeing it become narrow. If I make that negative, then it reflects that over the x-axis. If I make this number less than 1, the absolute value less than 1, so let's say I put a 0.5 in there, then now I get a wider graph than my original mother function. So I just wanted to show you this. You can see prior to even graphing something, you want to look at your original function just to determine what it should look like. Just be smart about how you start to graph something based off of its original equation. Okay, now if you are given a graph or something to graph and it's in standard form, the easiest form to graph something is in vertex form. So what we want to do is complete the square so we can transform it. So what we're going to do here, I'm going to move that 8 over to the other side so that I can focus on just those terms on the right hand side, negative 3x squared plus 12x. Alright, if we remember, what we do is we need to factor out the lead coefficient here, that negative 3. I do not factor a GCF, I just factor out the lead coefficient, and I'm left with negative 3 times the quantity x squared minus 4x. On the other side, I'm going to leave that as y plus 8. Okay, now the goal here is to cut that number, the coefficient of the linear term, cut that in half and square that number. So if I cut that in half, 4 divided by 2, and then squared, well, it's actually negative 4 divided by 2 and squared, it gives me a positive 4. So now I'm going to add a positive 4 onto the right hand side and balance the left hand side as well. So I'm left with y plus 8, I'm going to leave a space there, equals negative 3 times x squared minus 4x plus this new term here is going to be a positive 4. Now I need to make sure I'm adding to the other side a factor of negative 3 times 4, which is really negative 12, so that I can balance this correctly. Now I am left with y minus 4 equaling negative 3 times, and I'm going to factor this right hand side. I just completed the square, so I know that that square should be x minus 2 squared. And then just so that you get back into vertex form, let's add that 4 back over. So we end up with negative 3 times x minus 2 squared plus 4. Now when I go to graph this, I need to first identify some characteristics of the graph. I know that it's going to be a vertical stretch, and it'll also open downward because of that negative 3. I also know that my vertex is at 2, 4, based off of the equation that I just converted it to. So I'm going to go to 2, 4 and draw my vertex. So this is going to be a maximum value because this quadratic will open downward. Alright, so I can quickly translate the rest of those points. I know that normally I would shift left 1 and down 1, right? This would be my 2 normal points for the mother function, but since I'm stretching it by a factor of 3, this time I'm going to shift over to the left 1 and down 1, 2, 3. So that should be my next point. So I shift right 1 and down 1, 2, 3. There's my next point. For additional points, I also know that the next coordinate, if I had the regular function, mother function, so if I had y equals x squared, I just did 1, 1, right? That would be 1, 1 or negative 1, 1. Those are the 2 points I just did. I also can do 2, 4 and negative 2, 4. So that means if I go left 2 units from the vertex, instead of going down 4, I need to go down a factor of 12 because 3 times 4 gives me 12. So I'm going to go to the left 2 and down 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And I end up with a y-intercept here of negative 8. So there's multiple ways you can find that y-intercept. Of course, you could plug in x equals 0 into your function, but we just found it there as well. And then I can use the idea of symmetry here to find that other coordinate. It should be on the other side of that line of symmetry. Okay. I also neglected to mention earlier that our line of symmetry is given when it's in vertex form. You can easily tell the line of symmetry because the coordinates, or the equation that defines that line of symmetry, is given by your x coordinate. So in this case, line of symmetry is x equals 1. And that's just a really easy thing to tell if it's in vertex form. So here in vertex form, our line of symmetry should be x equals 2, and in fact, it is. Alright, let's work on the next one. You guys can pause this and try this problem on your own, and then check your solution with a key, or just listen to me work this out. Alright, I'm first going to add 1 to the other side, and I will factor out the 2/3. So I have x squared plus 2x inside my parentheses. And now I'm going to complete the square by taking this number 2 and cutting it in half and squaring it. So I cut that in half and square it, I just get 1. So now on both sides I'll leave a blank. I'm going to rewrite this as x squared plus 2x, complete the square, and write a plus 1 in there. Okay, so I just added that new term. Now I'm going to add to the other side, just to balance my equation, a factor of 1 times 2/3. So I'm going to add 2/3 over here. Now I'm left with y plus 5/3 equaling 2/3 times x plus 1 squared. And now I can subtract over that 5/3 to end up with this function in vertex form. Alright, to graph this, it's going to kind of be a little bit goofy because I have such weird coordinates, with the stretch being 2/3 and negative 5/3 is, our vertex, or y coordinate for the vertex, but we'll try it anyways. So we're going to go to negative 1, negative 5/3. Okay, so negative 1, negative 5/3 places it about right here. I know that this function should open up because this is a positive number, and it's also going to be wider than our mother function. So typically I would go to the right 1 and up 1 from this graph. So it would be somewhere, again it's approximating it, but about right there if I go right 1 and up 1. But I only want to go right 1 and up 2/3 of that. So let's work on a translated point, because I think that would be much easier to find the coordinate here if we just translated our point. Okay, so in our mother function, y equals x squared, we would typically have, our vertex at 0, 0, but one of those other first points that you would graph would be 1, 1. So I want to take this point and I want to translate it according to what we've done to our function. So when we look at this function, we have a stretch of 2/3. Really, it's a compression of 2/3. We are shifting our x-coordinate left 1, and we are also moving our y-coordinate down 5/3. So remember, with order of operations, you want to make sure, since this is affecting, this function here is affected in two different ways by the y-coordinate, we want to make sure we do order of operations first. So when we're looking at the y-coordinate, we need to first multiply this number here by 2/3. So our new point would be, well, our first step to getting our new point. Now we know it's 1 comma 2/3. Now I also need to move this down 5/3, so now our point becomes 2/3 minus 5/3 and ends up at -1. And for our x-coordinate, we need to subtract 1 from that value, so now I'm ending up at 0, -1. So it actually looks like this, and it's pretty easy to figure out where that point is if we just, plug that in. Alright, so I use the line of symmetry here, which is at x equals -1 to find that other coordinate. Now when I find my next coordinate, typically I would go right 2 and up 4 from my vertex, but this time, again, you need to work on your translations. So if I look at the y value, I need to multiply that 4/3 by 2/3. So 4 times 2/3 is why I get 8/3 here. And then I'm going to subtract away 5/3 because I'm shifting that function down. So if I take 8/3 and subtract away 5/3, I end up with 1. The last thing I need to do is make sure I subtract away an x value here. Oh, subtract 1 from my x value here to get the coordinate 1, 1. So that next point should be here at 1, 1, and I can reflect that over to get to this. Alright, so that's about 5 points. That's good enough for me. And that's the idea of what you're going to do when you see translations that, have fractions and kind of weird numbers in there. Okay, now in this next section, what we're going to be doing is finding maximum and minimum values for quadratic functions as well as quadratic-like functions. So this is a little bit of review for you guys, but there is a big idea here that's going to be brand new for you. So let's just discuss whether or not a function when it's a quadratic would have a max or a min. So if a quadratic opens downward, we know that the vertex should be the maximum value that's attained by the function. If a quadratic opens upward, then now this quadratic has a minimum value that will be attained by finding its vertex. Okay. Now the vocabulary terms here that you need to know are obviously max and min, but also how to explain them and express them. So when you want to talk about a max or a minimum of a function, the max occurs at the y value, or the max or min is the y value, but it occurs at the x coordinate. So when you're reading this out loud, you would say the max or minimum value is y, and it occurs at your x coordinate. Now, when you're given a function, let's say this problem here, and you're not given something in vertex form, you don't have to complete the square like we did in those other two problems. We just completed the square because it's easier to graph that way. In this case, all you need to do is use a little formula here that gives you the x-coordinate for your vertex. So the x-coordinate of our vertex is given by x equals -b over 2a, so the opposite of b over 2a. So what I'm going to do here is just take this, which is in standard form, and find the opposite of b over 2a. And in this case, I have 4 over 2 times 2. And I get my x vertex, or the vertex of the x coordinate of my vertex to be 1. So now I need to actually find in this case, this is opening upward, right? So I have a minimum here, and I just found the x coordinate. If I want to find the y value for that, I need to find f of 1. Okay, so f of 1 is going to be found by plugging in 1 into our function, and I end up with +5. Okay, so this is now saying that our minimum value for this function, so the minimum is 5, and it occurs at x equals 1. Okay, so basically up to this point, everything has been a review for you guys. Now we're going to get into something completely brand new. We are going to be determining the maximum or minimum value of functions that we don't necessarily know what they look like. Okay, but in each case, if you look at problems 4, 5, and 6, they look very similar to quadratics. So these are quadratic-like functions. The only problem I'm going to change here, if you guys can go down to number 6, let's change that to 2x to the 4th minus 4x squared plus 7. Okay? Alright, so first I want to take a look at the graph of 2x squared minus 4x plus 7. So remember, when we determined the minimum value, we said that the minimum occurred at x equals 1, and it was 5. And you can see right from the graph of this that we were in fact correct. Okay, now if I take a look at that next function that I'm supposed to find the max or min for, I'm noticing that this has a minimum value. Okay, it looks similar, I guess, to the graph of 2x squared minus 4x plus 7, but it's been shifted down a little bit. But I still have a minimum value. And then I notice that that minimum value has the exact same x coordinate. Okay, so the x input is the exact same here. It's at 1. Okay, so that x input is at 1. I don't know the y necessarily, but I do know that that input is 1. And then if I look at the cube root of 2x squared minus 4x plus 7, it's shifted down a little bit more, but I'm also noticing the same thing. That x coordinate, where that minimum occurs, is the same. So I'm noticing two things. One, they all three have a minimum value, and the minimum occurs at the same spot. And if I finally look at the graph of 2x to the 4th minus 4x squared plus 7, this one is in blue. This time I'm seeing also, I have maybe two minimum values here that occur at two different x's, but the one minimum does occur at the exact same x coordinate as my original function, 2x squared minus 4x plus 7. Okay, so let's use that idea now to solve. Alright, so it says to determine the input or output that produces the smallest or largest output for this function. Now, in your homework and in your tests and quizzes, you're not necessarily going to have found already the input before, right? We already found the minimum value for this quadratic. So what you want to do here, we're kind of cheating because we already know what that minimum value is. What you want to do here is take a look inside your radical and say, okay, that's a quadratic function, and that quadratic function has a minimum. So that means that this function should also have a minimum value. That minimum value will occur at the exact same minimum value that this function's minimum occurs at, which we already found, right? We said negative b over 2a was equal to 1. So what we now do to find our new minimum value, because this doesn't necessarily have the exact same minimum, it has the same input, we would now plug that value in and find f of 1 with our new function. So it would be the square root of 2x squared. Well, we already know the output here. I'm cheating, but we already know this output for 2x squared minus 4x plus 7 is going to be 5. So the minimum value here for our new function is root 5. Now, the original question, though, you want to pay attention to the question. It just says to determine the input or output. We already did that a long time ago when we just said it was equal to 1. We found the minimum value, which is root 5, but it didn't ask for that. Anyway, going on to the second question, now it does ask find the max or min. And in this case, again, you want to look at this analytically and say, okay, that's a parabola that opens up, so it will have a minimum value, okay? And the minimum occurs at the exact same value that this would occur at, you know, since it's a quadratic. I know already, and I'm cheating again because we already found that the minimum was at 1, so I plug in 1 and I find that the inside ends up being 5. So the minimum value here is the cube root of 5. Okay, so the minimum value of this new function is the cube root of 5. Okay, so now I'm going to treat this last problem as if we didn't know what the minimum and the maximum was. Okay, so for this problem, which is no longer here, I look at this problem and I say, okay, if I were to let t equal x squared, then that new function is 2x squared minus 4x plus 7. And then I say, okay, since this is a parabola that opens up, this function will have a minimum value. Okay, just because this function also has a minimum value. And then I try to find that minimum by first figuring out where that minimum occurs in this quadratic. So that minimum occurs at negative b over 2a. So I plug it in according to my function, and I get a minimum value that occurs at x equals 1. Then, to find the actual minimum, I need to take this value, this x, and plug that in to my function so that I have my minimum value at 2 times 1 to the 4th minus 4 times 1 squared plus 7. And I end up with 2 minus 4 plus 7 to get positive 5. So the minimum of 2x to the 4th minus 4x squared plus 7 is 5, and it occurs at x equals 1. Okay, that's the end of the lesson. Nice job!